we will first look at the MacCormack method for the simple case of linear wave equation first, and then we will add the diffusion term, which will make it a Burgers equation. And once we understand how to discretize according to the MacCormack method the advection term and the diffusion term, then we will go back to the vector form of the conservation equations, and we will apply this method to those. So when we consider the linear wave equation, we have dou phi by dou t plus c dou phi by dou x equal to 0 in one dimensional form, and we can, according to the MacCormack method, we can go from n to n plus 1 in 2 steps. And this is a stratagem which has been used by many people to go from step n to n plus 1 in 2 steps so as to increase the accuracy of the time differencing. We have seen that normally we have used forward in time for many of the discretization, and that is only first order accurate. If you want to have a time accurate resolution of the velocity field and the pressure field, we need to have second order accuracy at least. And if we therefore use a second order central in time, then it is not a self starting method apart from stability considerations. So the 2-step method, where you have a predictor step and a corrector step, will give us an algorithm which is self starting, which can be started from n equal to 0 or time equal to 0 with the initial and boundary conditions specified, to time equal to any time t of our choice. And we also make use of the predictor and corrector series of calculations to make it second order accurate in time. There are many methods, and MacCormack method is one of these methods, and in this the predictor step involves forward in time for this and forward in space for this. So we know that forward in space and forward in time or FTFS scheme is unstable, okay, but using that as a predictor step and then a corrector step which cures the instability associated with the FS forward in time is the total algorithm that we have in this. So we have the MacCormack method proposed in 1969 has an intermediate evaluation of the value of phi at n plus 1 bar step, which is given as phi in minus c delta t by delta x. We have taken this to the other side and delta t, and this is based on forward differencing of the space. This is called the predictor step. The corrector step evaluates phi I n plus 1. Now we actually get the value of phi n plus 1, this is only an intermediate value, takes this one to be the average of the two. So we have half of phi I n plus phi I n plus 1 bar, okay, and we have minus c delta t by delta x, which is this is in the predictor step. It is now evaluated as forward in time. Now we make it backward in time, phi I minus phi I minus 1, and this is evaluated now at n plus 1 bar. Okay, so you go from phi I n to phi n plus 1 in 2 steps. In the predictor step, you make use of this explicit FTFS scheme to evaluate phi I values at the intermediate thing for all I, and having known the phi I at n plus 1 for all I, we come to the corrector step in which we evaluate phi n plus 1 as the original value plus the estimated predicted value here, and a backward in space discretization of the space derivative making use of the predicted values of phi I at that intermediate step. So the overall scheme here is of second order accurate in time and second order accurate in space, and it is self starting in the sense that if you know the initial conditions, then you can start this and then you go on to this, and it is conditionally stable for sigma less than or equal to 1. So it is not unconditionally stable, but it is conditionally stable with sigma equal sigma, the Courant number, which is C delta T by delta x being less than 1. So this is one method which has proved to be popular. Now in our governing equation, we not only have the advection term, but we also have the diffusion term. So when we have an equation with advection term and a diffusion term, this model equation with constant C and constant alpha is known as the Burger's equation. MacCormack in 1971 extended to this method to include this case also, and the evaluation of this is relatively straightforward because we normally use central scheme for this. So and MacCormack also used the same thing. You have a predictor step which is given as phi I n plus 1 bar. All the predicted values are given with n plus 1 bar. So this is phi I n minus C delta T by delta x. We make use of forward differencing here plus central differencing for the diffusion term phi I n plus 1 n minus 2 phi n plus phi I minus 1 n, and the corrector step is very similar. Phi I n plus 1, this is the value that we are actually now seeking, is the average of phi I n plus 1 n, and the contribution coming from this, so that is minus half C delta T by delta x. Now this is evaluated as backward in space, that is phi I minus phi I minus 1, and this is also evaluated using the predicted values n plus 1 bar, n plus 1 bar, and this is evaluated again plus half of alpha delta T by delta x square. This is evaluated using central differencing, but with predicted values, that is phi I plus 1 minus 2 phi I plus phi I minus 1 at n plus 1 bar. Okay, so now this is the way to go from phi I n to phi I n plus 1 in 2 steps, each of which is an explicit step and each of which is used to evaluate for all I points at n plus 1 bar and then at n plus 1, which makes the overall solution as an explicit and is still second order accurate in time and second order accurate in space. But since we have made use of the diffusion term, the stability is not only given by sigma value, but also the diffusion term will come into picture in terms of determining the stability. Okay, let us not worry about the stability for the one dimensional case, because what we are interested is the general 3-dimensional case. Okay, so and we will try to describe what is the stability condition for the general 3-dimensional case, and this method has proved to be very popular, and we will see how this method can be applied to our governing equations, which are now written as dou u by dou t plus dou e by dou x plus dou f by dou y plus dou g by dou z equal to 0, where each of this u, e, f, g are column matrices containing 4 terms each, representing the terms which appear in the mass conservation equation or the continuity equation, x momentum equation, y momentum equation, and z momentum equation. So there are 4 terms coming in each of these column vectors, and they represent the 4 equations. Now you have an equation like this, and we can readily apply the MacCormack method to this, keeping in mind that the E term, F, G here, they contain both the advection term and also the diffusion term. Okay, so although we have written it as purely this method, this like this, it also includes both the advection and diffusion term, and we have to discretize them if we are using a MacCormack method in the proper way. That is, the advection terms as a combination of forward and backward, and the diffusion terms using central differencing, making use of the concurrent values, and the corrector step having an average value of this and an average value of the advection term and also an average value of the diffusion term. So in the overall phi n plus 1, there is some contribution coming from phi I n obviously here, and part of the contribution from the advection term is evaluated in terms of n, and part of the contribution is evaluated in terms of n plus 1. And similarly for the diffusion term, we have part of this is evaluated here and part of this is evaluated here. So this is seen as a correction to the value that is predicted using only the n values. Okay, so together this predicted evaluation of the diffusion term and the corrected one together will give the overall value of phi n plus 1. So you have a prediction and a correction that is incorporated for diffusion terms in a certain way and advection terms in a certain way, and we have to make use of these recommendations in evaluating this. So as per this, we can write down the predictor step in the following way. Ui n plus 1 bar is the predicted value. This is Ui n minus, we have this term, this is evaluated in the predicted step using forward differencing. So that is E I plus 1 j k minus E I j k n divided by delta x, and of course we have delta t going here, so we will just put this like this. And this is also evaluated in forward differencing in the y direction. So this is f I j plus 1 k minus f I j k evaluated at n times delta t by delta y, and this is also evaluated in forward differencing in the k direction. So I j k plus 1 n minus g I j k times delta t by delta z equal to 0. Okay. We have taken them on to the right hand side. We have, so this is the predictor step, which looks like a straightforward application of this method. Now we come to the corrector step. And here now we have Ui n plus 1 is equal to uin plus ui n plus 1 bar by 2. We note that this ui n plus 1 bar is evaluated for all of them, and now we have minus half delta t by delta x of this term evaluated using forward backward differencing. So that is ei jk minus ei minus 1 jk, and this is evaluated making use of the current known values minus half delta t by delta y. Again we make use of backward differencing ijk minus fi j minus 1 k at the intermediate values minus half delta t by delta z g I comma j comma k j comma k minus 1 at the intermediate. So we evaluate the value here in this way. Okay. Now this is a vector equation. Before we go into the evaluation of each of these E terms which have the mixture of advection term and diffusion term, let us look at the overall scheme. And so this step has 4 equations to solve, because U has rho u, rho v, rho w transpose. Okay, and similarly E has the corresponding terms in each of those things. So using these steps, we first evaluate ui n plus 1 bar. Okay, so that gives us rho n plus 1 bar, rho u n plus 1 bar, rho v n plus 1 bar, and rho w n plus 1 bar. Okay, so the predictor step will give us these, and we notice that the variables that are appearing are rho, rho u, rho v, rho w. Okay, and once we have these values for all I, then we go from this into the corrector step. Okay, through the corrector step to get ui n plus 1. That means we get rho n plus 1, rho u at n plus 1, rho v at n plus 1, okay. So if we get this, so we know rho at n plus 1, and this is so from this we get u n plus 1, because in this is rho times rho n plus 1 u n plus 1, and rho n plus 1 is known from this, so you get u n plus 1, and this is we get rho n plus 1 v n plus 1, again we know rho n plus 1 here, so from this we get v n plus 1, and from this we get w n plus 1. Okay, and we have so this gives us rho n plus 1. So the implementation of this particular method is that we first solve the continuity equation as per this discretization with taking the corresponding values of E, F and G from the continuity equation. Okay, for example, we have E will have rho u and F will have rho v, and G will have rho w like this. Okay, so if you want to, the first thing that we do in the predicate step is to solve the continuity equation as per this. Okay, so let us just write it down. So we get rho n plus 1 bar is equal to rho I n plus 1 bar equal to rho I minus the term that is appearing here is rho u I plus 1 times delta t by delta x minus in f we have rho v. So this is rho v at n I j plus 1 k minus rho v at I j k minus rho w at I j k plus 1 n minus rho w at I j k. So we solve this equation knowing the values of rho u v at nth time step for all points, that is I plus 1 I, j plus 1 j and k plus 1 k. So this is an explicit form, this is delta t by delta z. So this is evaluated for all I, and then we come to the corrector step. As rho I n plus 1 as half of rho I n plus rho I n plus 1 bar minus half of delta t by delta x rho u n plus bar, which is already calculated, I j k minus rho u at I minus 1 j k n plus 1 bar minus half of delta t by delta y rho v at n plus 1 bar I j k minus rho v at finally minus half delta t by delta z rho w at n plus 1 bar okay. So you can see that these are the equations that we solve to get rho n plus 1 bar and then rho I n plus 1. Now but here we see that there is a difficulty, whereas we can execute the predictor step readily. In order to get the corrector step, we need to know rho u n plus 1 bar at ijks and rho v n plus 1 bar ijks like that. So the way that we implement this equation is that the predictor step is applied not just to the rho equation, the continuity equation first, this is applied to all the 4 equations. Okay, so from these things we get rho n plus 1 bar, rho u at n plus 1 bar, rho v n plus 1 bar and rho w n plus 1 bar. So having applied the predictor step for all the 4 equations and having now evaluated rho n plus 1 bar and all these values at all ijk's, then we come to the corrector step, and then now we know these things because we have already solved the predictor step of the x momentum, y momentum and z momentum. Then we go into this. So there is a sequential process here that the predictor step is evaluated for all the variables, and we get the predicted values of all the variables here, and then we make use of this to implement the corrector step for all the variables, and then finally get the values here. And at each stage of implementation there is a hierarchy, there is a sequence. First we evaluate, first we apply this to rho, and then we apply this to rho u, and then to rho v, and then to rho w. So in that way we can go through the whole equations, the coupled equations, and then solve them sequentially, once through the predictor step and then through the corrector step in an explicit way, and finally get the solution for rho uv at n plus 1th time step from known values of nth time step. Okay, so this particular method is it makes a close linkage among the equations. Okay, that's why it works even though you have nonlinearities. So we are starting with known values of u, v, w and rho at all points. Okay, so after we know them, we don't go and straight away evaluate rho n plus 1. We go through the intermediate evaluation of rho n plus 1 bar here. At that point we are making use of u, v, w, okay, the old values of u, v, w, and when we come to n plus 1 bar we need the intermediate values of u, v n bar, u, v n plus 1 bar, which we solve by again by applying the predict step to the other equations. So that is, as we go from rho n to rho n plus 1 bar to rho n plus 1, we are not only updating rho, but we are also updating u, v, w and n plus 1 bar. So this intermediate updating of all the variables allows the nonlinearity of the equations to be properly accounted for, and that is why it seems to work for the combined set of coupled equations. We notice that when we want to solve the continuity equation, we need to know u, v, w, okay, and when we want to solve the x momentum equation, again we need to know not only u but also v and w, and the same thing goes for y equation and z equation. So in that sense, for each equation we need to know all the values of all the variables at the neighboring points, that is at I plus 1, I minus 1, j plus 1, j minus 1, k plus 1, k minus 1. So this need to know simultaneously everything makes the solution very complicated and very prone to divergence, and this way of doing it in 2 steps of delta t separated by a small delta t, that is going from n to n plus 1 bar to n, in which all the variables are evaluated and then corrected, will make the method work. Okay, so that is the advantage of this. This is an explicit method for the solution of all the partial differential equations together, and it is second order accurate in time and space, and it is conditionally stable. The stability is not only determined by the advection term, so that is by the something like the Courant number, but also by the diffusion alpha delta t by delta x square, and it is also determined by the fact that now we have 3 dimensions in space. So that is, we have the delta x term and delta y term and delta z term, and we have seen that when you go from 1 dimension to 2 dimensions for the pure diffusion case, then the allowable time step is reduced. Okay, now we have going to 3 dimensions and we have to get an overall stability criteria, which is not possible in the general case. Okay, so there are some numerical experiments done and approximate analysis done, which gives an idea of the possible time step that we can have for the combined solution of all these things using MacCormack method. Before we look at the discretization of each of the terms in E and F and all those things, let us take an overview of the method and then make a complete description of the method. We have written the governing equations, the Navier-Stokes equations, in the form of du by dt plus dE by dx plus dF by dy plus dG by dz equal to 0, where U, E, F, G are column vectors containing 4 terms each. We will come to those 4 terms, and once you have an equation like this, we can look at how the U, which is the variable of interest, evolves with time by going through a 2-step process to go from n to n plus 1 in the MacCormack method, MacCormack explicit method. And in this we write in the predictor step, we evaluate the value at ijk n plus 1 bar. This is the intermediate time step in terms of the value at the time step n minus the discretization of this using forward differencing. So that is delta t by delta x, the delta t coming from here will go there, and this is forward differencing, that is E I plus 1 jk minus E I jk. So this makes it forward in x derivative evaluated at nth time step, and similarly the dou f by dou y is discretized using a forward differencing in the y direction, that is f I j plus 1 k minus f I j k. So this makes it forward in delta y evaluated again at nth time step, and dou g by dou z is again discretized in the forward differencing in the z direction. So that is g I j k plus 1 minus g I j k, where g is evaluated at nth time step. So this enables us to get the value of u I j k at the intermediate step. This is an explicit step because all the values here are evaluated at the nth time step, therefore we know them, and we go through the evaluation of u at the intermediate time step for all the points ijk of interest, and then we come to the corrector step, in which we actually update from n plus 1 bar, that is the intermediate time step, to n plus 1, and this is evaluated again explicitly as half of u I j k n, which is the previous time step, plus half of u I j k at n plus 1 bar, which is evaluated like this, and then here we go back to backward differencing for each of these space derivatives. So we have delta t by delta x, we also have the half term because we are making a correction to the estimate that is made here, and this is E I j k minus E I minus 1 j k. This makes it backward differencing in x direction, evaluated now at n plus 1 bar time step. So these are the values which are obtained as a result of the predictor's time step, and when the terms within E are functions of the variables, then these are evaluated at n plus 1, and we will see that presently. Now again the dou f by dou y is evaluated again using backward in y, so that it is f I j k minus f I j minus 1 k, making this backward, evaluated at n plus 1 bar, and the dou g by dou z is also evaluated using backward in space, so that g I j k minus g I j k minus 1 evaluated at n plus bar and n plus 1 bar. So together these steps will enable us to go from u I n to u I n plus 1. Sorry, it has to be 2 I j k plus 1. So we complete the predictor step for all the points and all the variables, and then we come to the corrector step, by the end of which we get the values of interest. Now what are the components of u, E, f, g, so that this represents the Navier-Stokes equation. We are looking at the case where tau ij is expressed as dou u I by dou xj plus dou u j by dou xi times viscosity plus the second coefficient of viscosity times dou u k by dou xk, and we are neglecting the second coefficient of viscosity as being unimportant and also as being undetermined. So we have a tau ij given like this, that is for a Newtonian fluid, and under those conditions we can write down the components of u, which is the main variable of interest, as in the continuity equation we have rho, in the x momentum equation you have rho u, y momentum equation we have rho v, z momentum equation we have rho w. Now the E term, which represents the advection component coming from the x faces, the positive x phase and negative x phase, it has, in the continuity equation you have rho u, in the x momentum equation we have rho u square pressure and the shear stress, that is minus tau xx, which as per this is evaluated as minus 2 mu dou u by dou x, and the component arising out of the y faces will have the advective component rho u v, and tau yx, which is the shear stress, which is now given by mu times dou u by dou y plus dou v by dou x with a minus sign. So this whole thing is tau yx, and here we will have tau xz. So we have rho u v minus mu times dou w by dou x plus dou u by dou z. So these are the stress components which are appearing in the Navier-Stokes equations, which are also components of the corresponding elements of the E vector here. Okay, this representing the component coming in the continuity equation, x momentum equation, y momentum equation and z momentum equation. And similarly when you come to the F vector, this contains the net advective pressure and viscous stresses components acting on the two y faces, that is the top face and the bottom face. So for the continuity equation we have rho v, for the x momentum equation we have rho u v and then tau yx, that is minus mu times dou u by dou y plus dou v by dou x, and in the y momentum equation we have rho v square plus p minus 2 mu dou v by dou y, and in the z faces we have rho v w minus mu times dou v by dou z plus dou w by dou y, and finally the g component here is the sum of the term, is the set of terms appearing from the z directional faces, that is the front and the back face, and we have rho w in the continuity equation and rho u e minus the shear stress in the z direction, so that is tau zx, which is mu times dou u by dou z plus dou w by dou x, and in the y momentum direction we have rho v w minus mu times dou v by dou z plus dou w by dou y, and in the z momentum direction we have rho w square plus p minus 2 mu dou w by dou z. So the elements which are appearing in this u, e, f and g, when put together in this form, will give us a Navier-Stokes equations for a Newtonian fluid in which the second coefficient of viscosity component has very little significance, okay, has no contribution to make to the momentum equations. So, and the solution of these things will proceed as we have discussed. Each equation is solved using this method for all the points I, j, k, and then we go to the next equation, next equation, next equation. We complete the predictor step for all the points and all the 4 variables, and once we have these things, then that means rho n plus 1 bar is evaluated for all ijk, rho u n plus 1 bar is evaluated for all n plus 1 ijk, and similarly rho v and rho w. Having these things, now we go to the corrector step and then we employ these things, and for example when we say E ijk n plus 1 bar, okay, so the E here corresponds to this. So this whole thing is evaluated at ijk n plus 1 bar, and so the evaluation of u here and rho here is not a problem because these are at particular points, and p ijk is also not a point, but we have to be careful in that in the evaluation of the derivatives here. You have dou u by dou x here and dou u by dou y here and dou v by dou x, okay, and if you look at any of these EFJ components, you have either the same derivative or the cross derivative. The same or cross referring to the way that they appear in the governing equation that is written here. For example, when you consider E term, this is being differentiated with respect to x, okay. So a term like dou u by dou x, which will be because this whole thing is being differentiated here, will give you dou by dou x of dou u by dou x, so that is a normal derivative. And if you say dou u by dou y, which is also appearing in the E here, will be differentiated as dou square u by dou x dou y, so this is a cross derivative. Again this is a normal derivative and this is a cross derivative. So normal derivative, and here this will be normal derivative and cross derivative. And when you come to f here, anything with respect to y here will be a normal derivative, and anything with respect to x or z will be a cross derivative. In the same way here, anything with respect to z is a cross as a normal derivative, anything with respect to x and y will be cross derivatives, okay. So in that sense we have to make sure that the consistency of the evaluation of these derivatives, cross derivatives and normal derivatives, is maintained in order to maintain an overall second order accuracy of this discretization, because the overall evaluation of u ijk is second order accurate in both time and space. So in order to do this, we have a prescription in order to maintain the cross derivatives. Are evaluated using central differencings. Okay, and normal derivatives are evaluated using either forward differencing or backward, depending on how the main derivative is evaluated, okay. For example, in this term here, dou f by dou y is evaluated using forward differencing. So in the predictor step, the normal derivatives will be evaluated using backward differencing. In the corrector step, the same f is evaluated using backward spacing. So here one will use a forward differencing for a term like dou u by dou y here, okay. So forward differencing as per the evaluation of E, F, G, okay. And when I say as per, we should say as per the opposite of the evaluation of EFG, that is the normal derivatives are evaluated using backward differencing in the predictor step and using forward differencing in the corrector step. Okay, so it's only for the normal derivatives that this will shift. The cross derivatives are always evaluated using central differencing. Okay, so if for example we take a term like let us say this one here, okay, so this is f, and this is appearing at let us say ijk in the x momentum equation. This is appearing in the x momentum equation, okay, and this term will be let us say in the predictor step we want to get f n plus 1 bar. So we will just call this as the second component here, because the second component, and we want to evaluate dou f by dou y component here. Okay, so we want to evaluate this as it applies to the evaluation of this uin plus 1. Okay, so we have to evaluate this at n and okay, so ijk. Okay, so essentially what we are looking at is what is dou f2 by dou y as it appears here. Okay, ijk is evaluated as f2 n I comma j plus 1 k minus f2 n ijk divided by delta y. Okay, so that is what we have here. It is forward differencing. Now this f2 here has each of these components. Now for these things it is straightforward, so we can write the corresponding component of each of this, and we can say that this means that rho uv I j plus 1 k n is this one, if we consider only the first term here, minus rho uv I j k n by delta x. Okay, so the first term of this is written like this in a straightforward way. Now we come to minus mu du by dy. Okay, now we are looking at dou by dou y of this, so that becomes a normal derivative, and the normal derivative has to be evaluated in such a way that it is opposite to the way it is discretized for f, and here we have made use of forward differencing. So we have to evaluate this using backward differencing. So we can write this as, assuming that mu is constant, minus mu times so dou u by dou y at ijk using backward differencing would be, we will take the mu out and we can write dou u by dou y at I j plus 1 k n minus dou u by dou y at I j k n. Okay, so now this is the component arising out of this, and so this is evaluated using backward differencing, and this also evaluated using backward differencing, and we have this term here minus mu times dou v by dou x. So again we can write dou v by dou x at ij plus 1 k minus dou v by dou x at ij k divided by delta y. Okay. So this is the total expression of f2 ijk plus 1 of dou f2 by dou y term coming in this, and since f2 has 3 components, each of the 3 components has to be evaluated. So this has to be evaluated in this way. Okay, that is straightforward, there are no derivatives here, but you have derivatives here. So this term has to be evaluated this term is this term here, and again this term at ijk. Now here and here we have to use backward differencing. So we will write this as u at I j plus 1 k j plus 1 k n minus u I j k n by delta y. So this is the backward differencing of this term at I j plus 1. Okay. And similarly this term here will be evaluated as u I j k n minus u I j minus 1 k n by delta y. You can see that here this is a backward differencing approximation for dou u by dou y at ijk. This is a backward differencing approximation for dou u by dou y at I j plus 1 k. Okay, so because this is j plus 1 here, we seem to be getting a forward differencing, but this is actually a backward differencing when you evaluate this at I j plus 1 k. And this one here has to be evaluated using central differencing, and this one also using central differencing. So we can write this one here as v I j plus 2 k n minus v I. So j plus central differencing around j plus 1 means that j plus 2 and j will come by 2 delta x, and similarly this expression here will be v I j plus 1 k n minus v I j minus 1 k n by delta x. Okay, so in this way we can evaluate the individual terms which are appearing in this, making use of central differencing for the cross derivatives, okay, and using either forward or backward as per the opposite of the evaluation of EFG for the normal derivatives. So in this particular case dou y by dou f by dou y is being sought, okay, and this is being evaluated using forward differencing here. So that the normal derivatives which appear in this, that is this is a normal derivative because it is dou by dou y, so that will become dou square u by dou y square. So that is being evaluated using backward differencing, okay, at each of these points, and this term is being evaluated using central differencing. So the cross derivative is being used evaluated using central differencing. So that central differencing or backward differencing has to be evaluated for each f evaluation at that particular point. So here we are applying backward differencing at j plus 1, that gives us j plus 1 minus j, and here we are using backward differencing at j, and that gives us j and j minus 1, and here we are using central differencing centered around j plus 1. This is dou v by dou x, so this should have been j plus 1 and central differencing around dou v by dou x. So this is v I plus 1 j plus 1 k minus v I minus 1 j plus 1 k by delta x, and again this is dou v by dou x at ijk. So when we apply the central differencing around I here, so we will get v I plus 1 j k n minus v I minus 1 j k n divided by 2 delta x, and here also we have 2 delta x here. Okay, so now we can substitute this here and substitute this here and get an overall expression, and substitute this here and substitute this here and get an overall expression, and that will give us the evaluation of dou f2 by dou y at the predictor step in for the x momentum equation, because we are considering the x momentum equation. And if we were interested in the corrector step for the same term, okay, if we are interested not in n plus 1 thing but as appearing in the corrector step, so that is n plus 1, then this would have been evaluated in using backward differencing j and j minus 1. So here we would have to use forward differencing and forward differencing, and here we would be using still the central differencing. So by doing this consistently, we can get a set of equations using which we can march forward in time in the predictor step through all the points ijk to get n plus 1 bar, and then come to the corrector step and again march forward in time, march forward in ijk directions to get n plus 1 values, and from these we can get these things. Okay, and once we have rho u and so on, we get rho first, and from rho u we divide by the rho value to get u, and we divide by the rho value here to get v, divide by the w value to get here, and pressure is obtained as a function of density and, for example, temperature. And we have assumed isothermal flow here, but for a general compressible flow we will have to also solve for the energy equation, which we have not derived yet, and the incorporation of the energy equation to the calculation is very straightforward. We will have an additional variable here and additional set of terms coming in the energy equation, and those can be solved together with this. Okay, so this is how we can make use of the template, a given template for the simultaneous solution of the Navier-Stokes equations, or an extended form of the Navier-Stokes equations when we consider even the energy term. So, and this is how we can solve the set of the governing equations using one template. Now, will this work? Will this work in all cases? So that is the question that we will address next.